favorites because it lets you see homemade the behavior of a capacitor in a circuit. So obviously when you see the title RC circuits, you would know that we're going to discuss the charging and discharging of a capacitor. It's a very easy way to see it. We're going to provide the RC circuit with a constant voltage like a battery or a constant power supply to see the charging. And then for the discharge, the voltage is obviously going to be 0. So you will see the exponential behavior on a voltmeter, which can be found in any lab, any house. So that's why I call it homemade. We're not going to use any sensor. We're not going to use Data Studio on purpose because we want through this experiment to show you the slow behavior. And for slow behavior, we're going to use a very big resistor to make tau big enough for the process to be slow enough for it to be visible in the naked eye. So that's why we don't need any sensor. The objective of this lab is to study the time constant of the circuit. So all our focus would be on the time constant. So the only two measuring tools would be the stopwatch. That's digital. Any stopwatch would do. Your smartphone could be one of the ways to use in the lab, or any digital stopwatch given by your lab instructor that is of the same precision as your smartphone. I'm talking about the smartphone because you have it in front of you, and probably by looking at it, you would tell what is the precision of it. Since the values will be given to you, you can see how many decimals are given to you, and therefore you can tell what is the uncertainty on every measured time. This is measuring tool number 1. Measuring tool number 2 is a voltmeter. You're not really going to measure the voltage, but you're going to observe the voltage. You need to know what is Umax. You need to calculate 63% of Umax, and you need to calculate 37% of Umax, and measure the time until you reach them. Okay, so the voltage will not be recorded, but it will be used as a reference to measure the time. Okay, and definitely the variable here is the different R used and C used. Okay, I'm gonna start with a very simple circuit and probably ask some of you. Let's discuss this circuit that we have, and I don't know if I can use our Blackboard with a list of names, because it's wrong to target the students who are in front of me. I would love to talk to everyone. Is that your class, by the way? I think so, yes. I cannot see Sherbel with us. Sherbel is very loud. I cannot hear Sherbel. It means Sherbel is not here. Yeah. All right, Jad, I've been correcting a lot of your lab reports this morning. You received 3 grades today, right? All right, so Jad, let's discuss this circuit. What we can see here is a battery or many batteries or power supply. We have a resistor, we have a capacitor, and we have a switch. Just simply tell me, if I put the switch on A, do you think the capacitor is going to charge or discharge? This is very easy. This is grade 11 level, right? So it's going to be charged. What about if I put the switch on B? Discharge, obviously. In the lab, we're not going to do this. We're not going to use any switch. We will actually do a circuit where we have a battery and then remove the battery. So as you can see, when the switch is on A, it's going to be charging the capacitor. When the switch is on B, it's going to be discharge of the capacitor. Thank you, Jad. I don't know if Abdo is there. I want to discuss with Abdo the actual behavior of the tau, the time, the time constant of the circuit. Okay. Thank you, Ian. Thank you so much, Habibi. All right. How do you find tau? Is Abdo there? Can I see Abdo? Can I talk to Abdo? Not available. Roy, probably.
Yes, doctor.
All right. Roy, how are you today?
I'm fine. How about you?
I'm good, but I freak out every time somebody knocks on the door. I'm the only adult in here, and Dream is 7 years old. She opened the door alone. I freaked out, so now I'm breathing because I know, it could be any stranger. All right, so
yes.
How do you find the time constant of the circuit? I'm talking charge, discharge, anything. How do you define it? So tau, I'm
It's
talking about
equal
tau. Yes.
RC, resistance times the capacity.
All right, the capacitance. So R times C could be a way to find the value of the time constant of the circuit. Is that during the charge or the discharge?
During both, isn't it?
Yeah, because it doesn't matter if it's happening. All right. Another question. Is there any way to measure tau other than the fact to use, is there any way to measure tau? How do you measure tau?
Measure it like via a graph, graphically. We can determine
Graphically
tau.
could be a way to find tau. Yes. Let's say graphically, what would you plot to find tau?
V versus T at the time.
All right,
V
you
being
mean the
voltage.
potential difference across the capacitor as a function of time. All right, during the charging, let's say you will get this. How do you find tau? By the way, this is a review for you. I know you know this from high school, so this is basically a quick review for you. Yes, remind us, how do we find tau?
So during the charge phase, it's at 63% of the voltage.
All right, so you find
The
U
maximum.
max, which is this point, and you calculate 63% of U max, and you use the graph to find the time. This is a way to find tau graphically. By the way, do you remember how much time it takes the capacitor to be considered fully charged? And fully charged is basically 99.99% because it's always have an asymptotic behavior, especially that experimentally things are not gonna be perfect, which means you may not reach your max fully, because of some leakage happening and so on. Yeah, so do you have an idea how much time it takes to be considered fully charged?
No.
All right.
I can't remember.
So basically Hussein is saying 5 taus. Yeah, 5 taus can be considered full charge. Thank you so much. This is one method to find tau graphically, and graphically is considered experimentally. Can you think of another method, Roy? Probably Guy? Probably anyone? How do you find tau experimentally? Time needed until I is 0. All right, so if you measure the time needed until the current goes to 0, this would give you tau, right, Yara? It would give you 5 taus actually, because the current would go to 0 and the charging process is over. Yes, so and then you divide by 5. This is also an excellent experimental method to find tau. However, it's not very practical because sometimes it takes you forever during the waiting process because experimentally things are not perfect and the current may never go to 0, so the behavior at the end of the tail is not, it sometimes is weird, like it's not following the theory because of probably the power supply you're using. So it's not safe experimentally to target 5 taus. Let's target 1 tau only. Anyway, I was expecting people to discuss probably the tangent. You can draw the tangent to find tau, the tangent at time 0. You can simply, instead of using the graph, you can simply use a stopwatch and a voltmeter, which is very similar to the graphical method. So method 1, graphically 63%. Method 2, the tangent method. Method 3, you measure the time with a stopwatch and the voltage with a voltmeter and you find tau. Now tau equals RC, I'm gonna call it the theoretical method or the calculated method. Now let's discuss a bit something that we already did. This is the charging RC circuit. So you can see that Q increases with time exponentially and the current would go to 0. We don't have any means to measure Q, and since Q is proportional to U, you will actually measure U with a voltmeter or the potential difference across the capacitor only. I'm going to show you how the circuit could be confusing a bit to you. And then 63% or 63.2% of the maximum value will give you tau, all right? Same thing would go for the current. Since the current is a decreasing exponential, you follow 36.8 or 37% of I max. So you can plug your ammeter in series with the capacitor and measure the current at any moment, okay? All right, now for the discharging circuit, for the discharging curve, the circuit is gonna be a bit different. I'm gonna ask, let me see, Hussein to help me out. Hussein, how can I change my circuit to make it a discharging circuit? So I'm gonna cross out charging and I want a discharging circuit. How do you do it?
I'm gonna have to disconnect the battery.
All right, remove the battery. So cross out, open the circuit, remove the battery. What else? By the way, I have a voltmeter in here because I need to monitor what's happening to my capacitor. This is a voltmeter in parallel with my capacitor, all the time plugged in. Yeah, what else? You will, when you remove the battery, you will see the voltage across the capacitor is gonna start decreasing a bit. Then what do? Hussein? You start recording the time?
Yes, I'm gonna start recording till I reach like 36%.
All right, you will notice that you will never reach the 37%. Anybody can say why?
Mm-hmm.
Yes, the voltage is gonna decrease, but you're gonna wait forever for it to reach 37%. And you were gonna think that probably there's something wrong in the circuit. And yes, there's something wrong in the circuit. This is not a discharging circuit. Something is missing. Anyone can guess? Maria, Lynn, Karen, Yara, Hussein, Muhammad, Nagam, Iman, Aya. Remove the R. If I remove the R, the capacitor is not gonna be affected. By the way, removing R, I forgot to tell you that R is huge in this experiment. You're gonna do 220 kilo ohms and 100 kilo ohms. So we're talking above like thousands. We want big R's because we want the process to be slow. Otherwise, you cannot handle it as a human. If it's really fast, you don't have the time to time it. Add something that consumes voltage. I don't want to change my circuit. Remember, tau is R times C. So R is a constant, C is a constant for this experiment at the moment. Do you believe that's a circuit? If you remove the battery, you have an open circuit. How can you have a current? Something is missing. I need a wire, you guys, to close the circuit. Yes, I need to close the circuit. Otherwise, the capacitor cannot discharge itself. Probably, Hussein assumed by removing the battery, probably he said remove the battery and thought connect the wire again, all right? I know this sounds trivial, but a lot of students would remove the battery without connecting with the wire again. They will be confused because they will see that the voltage is decreasing. The voltage theoretically should not decrease because the capacitor cannot empty itself. However, experimentally, you have some leakage in the atmosphere. I don't know. You will see a very small decrease and you would think this is discharge. Discharge will only happen whenever you connect with a cable for it to start discharging in the resistor. Okay? So yes, discharge is gonna happen and now the curve is gonna look different. So you're gonna see exponential decrease. You need to target the 37%. Yeah. And the current is also gonna be decreasing. However, the current is gonna be negative because the charging is in one direction, the discharge is in the opposite direction. So if you want, you can simply put minus for those values. If you have an ammeter, which is not in our case, if you have an ammeter, you will see that the value of the current is going to become negative. This is assuming you're not touching the ammeter. It's there and you're not going to move it. Let's say you have an ammeter in parallel with all with R and C. Let's say this is an ammeter, but we're not going to do any ammeter. All right, so I forgot to tell you or to discuss the following, that you will be dealing with R1, you will be dealing with R2, you will be dealing with C1 and C2. I will show you the lab report in a moment. So you're gonna pick a combination, R1 with C1, do the experiment, find tau for the charge, then repeat for the discharge. And then you're gonna do R1, C2, charge, discharge, R2, C1, charge, discharge, R2, C2, charge, discharge. Then you're gonna do C1 and C2 in series with R1 and do the charge, discharge, and then C1, C2 in parallel And with R1, by the way, R1 is always in series with them, and you're gonna find the charge and the discharge. So all these combinations, okay? Now let's compare a bit the different circuits. So what happens when you have a bigger tau? Like for example, can you guess in this case, which graph has a bigger tau? The blue, the red, or the black? And all right, so Yara is saying the blue graph has a bigger tau. Okay, we can do the tangent at 0. You can do any method you want to find tau. Genti is saying the blue graph has a bigger tau. Karine as well. Yara as well. All the girls are saying blue. Boys, do you agree? So the question is, which graph has a bigger tau? Hussein does not agree. Sure, the girls agree for blue and the boys agree for black. Think again, people. Roy is saying black. Wow, this is so funny. So boys versus girls. I never thought this will end up like this. Now the girls are changing. So Yara, can you speak up and tell me why you changed your mind? Genti's changing.
Yeah, because I saw the legend and it says RC3 is 0.2 and the other ones are smaller.
How can you see the legend? I'm actually hiding the legend. Seriously?
I see it for some reason.
Yeah, and I thought you can see my screen. Ya Allah, I thought the boys just changed your mind because they have an effect on you. All right, so probably Genti can explain other than the fact that you saw the legend. I thought I was smart hiding the legend. Genti, can you explain why black has a bigger tau? Okay, so listen, this is a common mistake. When you see a fast behavior, you would think tau is big. Remember, tau is big when the behavior is slow. All right, so no need to do tangent, neither is 63%, although both methods are fine. Just think about slow and fast. Blue is so fast. Fast means a smaller time, okay? I think you guys thought fast means bigger time. So yeah, mistakes happen. So basically, yes, this is just a behavior to see how things are actually doing. A quick reminder about series connection. C equivalent is 1 over C, so you add the C's, and C in parallel, you can add the C's and not the inverse. By the way, it's the same thing for tau, assuming R is the same. So if R is constant and I have parallel and series with the same R, you will notice that tau that you will find for the parallel connection will be tau 1 plus tau 2, and tau that you will find for the series connection is 1 over tau to be equal 1 over tau 1 plus 1 over tau 2. You can use that to discuss the fact if you have a series or parallel connection. I need to show you the lab report. It's not in this presentation. By the way, I don't know if this is visible. I believe this is important to show you what I did for the experiment. First of all, I did not use a battery. Okay, please look here. This is really important. The batteries, I removed them. I don't like them. As you notice that I'm not using the battery neither for lab 4, neither for lab 5. Why? Because I don't trust their behavior. They don't show any constant behavior. And whenever you're doing a charge and discharge, suddenly at the end of the charge, they stop pushing constantly. All right, which give you a tail of the chart that is too long, and which means it's going to be very confusing for you if you're going to wait for 5 tau. So instead of using batteries, I used a regular power supply. The batteries are supposed to provide 1.5 volt, 1.5 volt in series 3 volts. I can read 3 volts all the time. Sometimes I have a fluctuation, 3 volts or 2.9, but trust me, this is constant. It's gonna stay 2.9 throughout my experiment. Now my voltmeter, this is a screenshot from the video. So in the video you will see the voltmeter is connected to the capacitor only. And this is the stopwatch I'm using. You can have a look. This is 6.19 seconds. Just for you to have an idea, digital uncertainty, think about it. Now let me show you the circuit. You have power supply. Okay, let me use a pen, thin pen. You have a power supply, then you have a wire. You see the wire? Then you have a capacitor. The blue guy is a capacitor. Then you have a resistor. Then back to the power supply. So this is a series connection. I connect my voltmeter across the power supply, the capacitor only. 2.9 is Umax. 63% of 2.9, let me see, 0.63 of 2.9. This will give you 1.827. So I would want to use a voltmeter to measure the time between 0 and 1.827 volts. By the way, I need to start from 0. And how do I start from 0? I need to short circuit my capacitor. Short circuit the capacitor means put a very tiny wire on top of it in parallel with it. It will directly empty itself in the wire to be 0. You will see it 0 on the voltmeter. I will show you in a minute on the video, fast forward. Get ready with my stopwatch. Reset. Start as soon as I remove the wire. By the way, in this box, you have a lot of tiny wires to use. Okay, let me show you the discharging circuit that students find a bit confusing, and then we can do the experiment and then show you the lab report. Okay, so how do I do the discharging circuit? First of all, I need to remove the power supply, and you see those wires are on the desk, and there's no power supply in here, and I should not forget to connect the place of the power supply with a vacant wire, with a wire, you know, because I need my circuit to be closed. Also, I need to start from Umax, which is 2.9, down to 37%. So 2.9 times 0.37, this will give me 1.07. So I should time between 2.9 volts down to 1.07 volts. How do I start from 2.9? I'm not supposed to charge my capacitor and wait for it to forever to be charged. What I can do is I can simply take my power supply and put it across the capacitor, directly across the capacitor. It will charge itself instantaneously because there's no resistance. Tau will be 0. So instantaneously is good. I need a partner to help me. So my partner will hold the power supply on top of the capacitor. Get ready with a stopwatch. 1, 2, 3. I start timing simultaneously while my partner will remove the power supply. So you would see the voltage decreasing from Umax down to any value you want. Okay. I will explain it in the video. Let me show you the video is ready. Let me see if it's visible. I'm not sure. So I'm explaining a bit what the board is. This board has been used in lab 4. So I'm sure that you know what I'm talking about. I'm explaining how, what is the capacitor, what's written on it. I'm explaining, this is another capacitor as well. So you can see it's written on it 330 microfarad and 100 microfarad. This is a nominal value, and I don't know how much you can trust a nominal value. A lot of students in the lab would ask for an LCR meter to measure the actual capacitance of the capacitor, and they would discover that the capacitance is a bit far from what's written on it. This is a resistor. I'm showing you the color code and telling you that one is 100. So this is 220 kilo ohms, red, yellow, which means 2 and 4 zeros. 220 kilo ohms. And the other one was black, brown, or brown, black, brown, black, yellow, which is 1 0 with 4 zeros. Okay, so I'm gonna be using those. This is the stopwatch. I'm also explaining the precision of it. Now this is the connections. I don't care about the connections because I already showed you the connections. I want you to see how I start the timing. I'm showing you the tiny wires. I'm proud of them. I don't have many, and I think they're very efficient to use. All right, let me show you how I short circuit. All right, I'm getting ready with my voltmeter. I think the voltmeter is on 2 decimals, or which means scale 20 volts. Okay, now let me show you how I short circuit. Okay, you see, I'm explaining the fact, where is it? Okay, explaining again. All right, you see, so I short circuited the capacitor on purpose because I want to start from 0. The capacitor would be it will fill itself so quickly. You cannot start from 0, you have to empty it. And this is the best way to empty it while being able to control your circuit. You can simply take the terminals of the capacitor and touch them together, you know, but then you will have to put it in the circuit and get ready with a stopwatch. So usually using a wire to short circuit the capacitor is very efficient. With another hand, because I don't have a partner in here, I will get ready with my stopwatch, 1, 2, 3, and remove the short circuit as soon as I click start for my capacitor. So I do it simultaneously. And you will see, I don't know if the thing is timing. All right, anyway, I'm explaining, showing you how I reset. I'm repeating, I'm showing you Umax. So you watch the video later. Okay. All right, now what I did, I removed the battery, you see, and I closed the circuit. While talking, the capacitor will start discharging itself. And I want to time from Umax. This is why I need the power supply. You see, the power supply is fluctuating between 2.9 and 3 all the time, which is not a big fluctuation. Now I'm going to use the power supply to touch the capacitor because I want to start from high voltage. Okay, I'm trying to pause to show you that the voltage, you see, the voltage is 3. 3 or 2.9, it's basically the same. This is a measuring tool and this is another measuring tool. This measuring tool gives you 1 decimal. This measuring tool is giving you 2 decimals. So this is more precise. Okay, sometimes we don't trust the screen of the power supply, but it's not bad. Like 0.1 is okay, you know, it's a good precision. Thinking of what measuring tools we have. So when I touch with the power supply terminals, the capacitor is gonna it's gonna charge itself instantaneously time 0 because I have no resistance or the resistance is negligible of the cables. I'm gonna get ready with the timer. I don't know if I can do that because both my hands are busy. I will remove the power supply and start timing instantaneously. I did not show you because it was impossible. However, it is possible if I do the following. Like I can keep the blue one inserted in the capacitor to free one hand, and I can remove only the red. I don't have to remove both for discharging to happen. So one person can do the experiment. You don't need a partner. And you will see that discharging is happening. If you watch the video, you can see that the discharge is pretty slow depending which resistor you're using, okay? I don't think I did the series and parallel. I'm only explaining that parallel means I will put the capacitor 2 on top of capacitor 1 on the same springs. That's parallel connection. Series connection would be I would want to open up the circuit a bit to make some place for capacitor 2, and that's it. Okay. However, the voltmeter should be on both capacitors, 1 and 2 together on the equivalent one. And that's it. You see, the experiment is easy. Now, if I go to the lab report, which is here, lab report, I'm opening the manual. You don't have a lot of data analysis to do. Basically nothing, just discuss. Just a second for the manual to open. Okay. Yeah, I was working. Where's the manual? Here. Sorry, all the windows are open. I'm not done. Okay, let me show you what to expect. First of all, they want you to answer some fill in the blanks question, like conceptual question. Then they want you to sketch. And by the way, please, sketch does not mean plot, because sometimes you have 2 points. If you have only 2 points, you can plot a straight line. If you have 3 points, you can plot something that would not be the behavior. Sketch means the whole behavior, which means draw the shape of the graph without plotting. Okay, how do you know the shape of the graph? By the way, this is voltage as a function of time. Talking charge and then discharge. You know it's exponential, so simply do the work showing the whole shape. Okay, because I already said for probably the team of Jad who did the sketch for the bulb, they already have 3 points on the table. They use the 3 points to do a plot and not a sketch, and they did not show the full behavior, definitely, because 3 points are not enough to show the whole behavior. But I know Students don't like to sketch because they want to be perfect, and sketch is only an approximation, it's an estimation. People, sketch means estimate, and it's okay to estimate. We need to describe the behavior, you can describe it in a paragraph, and it's okay to have an qualitative approach. I know you hate qualitative approach, you want a quantitative approach, you want measurements, you want plot. No, sketch means draw the shape with a pencil, okay? Sketch would be more meaningful if you show 1 or 2 values, at least U max, or at least an idea what tau is, okay? So add a point on this graph to have an idea of the order of magnitude of things. Are we talking milliseconds? Are we talking volts, millivolts? Are we talking 1000 volt or 10 volts? Are we talking 3 volts or 15 volts? So order of magnitude would be good for the sketch. Then you will be given a table where you have R1 with C1, R1 with C2, R2 with C1, then R2 with C2. You have the time of the charge, so it will be given to you. I will do the charging process and I'm gonna time it with 2 decimals. Time of the discharge, same. What is the average? This is not an average, this is only the mean, because tau of the charge is one experiment. Tau of the discharge is a different experiment. So I cannot say average unless I'm doing the same experiment again, and I call this trial 1 and trial 2. We're not supposed to find the mean, neither the average, but something would happen experimentally. I think time of the discharge is more accurate if you compare both to the theoretical value. I don't know why. I think the power supply will induce a lot of errors, sources of errors on your setup, on your circuit. You can discuss this later, by the way. So if you want to discuss what happens to tau, you'd rather take not tau C, neither tau D, but the mean, because you need to discuss if the mean is proportional to C or not. So tau C or tau D will be misleading, but taking the mean would be easier for you to analyze. Like here, they want you to do the experiment for the series and parallel connection and find the average. And if you want, you can simply remove average and write mean, because average for me is when you take the average of n values, talking of n a big sample of different trials, yeah? Yes, same formula, you just add them divided by 2. But some students would think this is average and they would do RMS. No, don't do that. This is only the mean value. Like you did both experiments, you don't trust this one, you don't trust this one, you take the mean, that's it. Yes. All right, so how does the increase affect the time? Charging and discharging time. This is why I would need this value, whatever you want to call it, and not this one or this one, because those are misleading. If you believe tau C is not misleading and tau D is not misleading, you can discuss using both. But if you believe they're misleading, and in some benches it was misleading, because every bench would give different measurements, that's why the students were required to find the mean, the average, the median, whatever you want to call it, okay? Then what happens to the total capacitance in series and in parallel? Probably you can calculate, discuss your data of tau and so on. And some conceptual questions. We're adding a lot of conceptual questions because we need to target your conceptual understanding along with your data analysis, okay? And that's it. You see, the lab is pretty small. You have one table, no data analysis to do. So just be careful with how many significant figures you're dealing with. And every time you need to discuss increase, decrease, proportional, look for constant ratios or constant products, okay? Don't say, and I have this with other classes, not your class, this value increases with this value, therefore they're proportional. Sometimes they're not proportional. Like for example, I'm trying to think about what you had in the capacitance experiment. No, you didn't have issues. By the way, your lab reports are perfect. I don't know if it's you were well trained through physics 302, or probably because you have previous's, which is okay, as long as you make sure you understand, and as long as you make sure sometimes the lab reports are a bit different. So target the understanding, and this is what I really care about. Okay, so you have a short lab report, you have an easy experiment. The the circuit is somehow confusing, but you're gonna be okay. I made sure to discuss the circuit on twice, once during the PowerPoint and once on the video. Let me know if you find anything confusing. Lab 3. Genti, I started with lab 3, but I did not finish it. Please don't freak out every time your grade doesn't show. If your grade doesn't show, it means I did not correct it, okay? Because I receive every week more than 10 emails about grades not showing. People, I'm slow. I'm very slow. I'm the slowest instructor on planet Earth with the grading, not with everything else, only the grading. So I take my time, I read it all, and I'm not gonna improve. I'm gonna be slow forever. The midterm. So far, I did not receive a lot of feedback from you. For concerning the midterm, I sent an email asking for feedback. I was surprised to see only 2 students replying, which is good, by the way. Tonight, I'm gonna focus on this matter and create a timing for us to follow. Okay? Yes, Yara. It's not a bad thing if there's no feedback. No feedback means you have no conflict, right? Karine, I would love to hear your alternative, but please don't publish it. Talk to me privately because publishing it will be confusing for your friends. Send me an email or a private message on WhatsApp and let me consider it. Don't worry, I will share it with the class. All right? If anyone would like to send, let me stop recording. If anyone would like to send an alternative